Hello everyone, welcome to the video lecturing on machine learning. So in this video, we're going to start with the module number 4, which is called as Bayesian learning. So in the last video, we have seen about the module number 3 and we have completed the last portion of module number 3, which is on the perceptron training rule as well as on the gradient descent rule. Okay, we have seen the two rules for weight adjustment in the perceptron. So that completes the third module, and today we will start with the fourth module, which is called as Bayesian learning. So before going to the Bayesian learning, first we should have some look at some introduction about the Bayes and Bayes theorem and what is Bayesian methods. Okay, so Bayesian learning methods are relevant to our study of machine learning for two different reasons. The first one is it will explicitly calculate the probabilities for hypothesis. Okay, so the main aim of this Bayesian learning is it will calculate the probability, and as you know that the probability values varies between 0 to 1, and if the probability of any hypothesis is 1 or nearer to 1, that hypothesis we will consider it as a best hypothesis. Okay, so Bayesian learning always points to the probabilities. So if you are well known with the concept of probabilities, then this becomes easier for you for learning this Bayesian methods. And second reason for why we are using this Bayesian method is we know that in the learning of many algorithms here in the machine learning, we do not have explicitly manipulate the probabilities. But here in the Bayesian learning, we can apply the probabilities rules for each and every algorithm to check which algorithm is giving the correct hypothesis where it reaches to 1. So probability values are varies in between 0 to 1. So if the probability of any hypothesis in the algorithm is considered as 1, that is called as a best hypothesis for our problem. So a scientist by the name Michi, he has given some detailed study about the classification by using naive-Bayes classifier and other algorithms including decision tree, neural network algorithm. So these researchers show that naive-Bayes classifier is competitive with other learning algorithms in many cases, that in some cases it outperforms the other methods. So what this Michi has done the study is, he has compared the different algorithms that you have studied already: decision tree algorithm, neural network algorithm, that is ID3 algorithm, and back propagation algorithm. He has compared this algorithm with another algorithm which is called as naive-Bayes classifier. Okay, and he found that in some of the cases this naive-Bayes classifier has proposed or produced good results or best results than other algorithms, other neural network algorithm and decision tree algorithm. So hence what he has decided is, he has decided that he will apply this naive-Bayes classifier for each and every algorithm to check whether the algorithm or whether this comparative study between the naive-Bayes classifier and other algorithms, whether this naive-Bayes classifier is giving good result or other algorithms are giving good result. What are the features of this Bayesian learning methods? So this features of this Bayesian learning method includes, so main thing is here is the final probability. Okay, if the final probability or if the probability value is near to 1 or equal to 1, that is considered as a best hypothesis. So here what we will do is, we will take each training example and we will estimate the probability of that training example, and if the probability is good or if the probability value is very high, then that hypothesis we will consider it as a correct hypothesis. Okay, so this provides a more flexible approach to learning than the algorithms that completely eliminates the hypothesis if it founds to be inconsistent with the single example. So we have seen the previous algorithm where if the hypothesis is not consistent with the training example, what we will do is we will eliminate that particular hypothesis. But here in this Bayesian learning, we will not completely eliminate the hypotheses which are found to be inconsistent. we will add something or we will delete something from the hypothesis so that it can be made inconsistent. It can be made with consistent with the training example. Okay. Next is prior knowledge can be combined with observed data to determine a final probability of hypothesis. So, if you want to determine the final probability of the hypothesis, you should have some prior knowledge of the data. Okay, which kind of data you have given, what kind of data it is suggesting. So, all this prior knowledge, okay, you should have, and then you can apply the probability to get the final probability. Okay, so we should have a prior probability for each candidate hypothesis. Then we should know the probability distribution over the data for each of the possible hypotheses. Bayesian methods can be accommodate hypotheses that can make a probabilistic predictions. For example, the hypothesis such as this pneumonia patient has 93% chance of complete recovery. So he has given a word, or he has given in a percentage that 93% there is a chance of recovery. So how we can correctly tell that there is a chance of 93% recovery. So it happens because of the probabilities. Okay. So here 93% is nothing but 0.93. So when we apply the probabilities on each of the hypotheses, we can observe the data distribution. We can observe the possible distribution across the data. So then we can predict that what is the chance of getting recovery. So we can apply this for other patients also, like heart attack patient, cancer patient. Is there any form of recovery happens? So if we apply the probability distribution on the data, if we collect the data of cancer patient, or if we collect the data of any particular disease like heart attack or any patient, so then if we apply the Bayesian methods for that particular observable data, then we can predict that whether that patient can recover or not. Okay, so nowadays many of the hypothesis or many of the datas can be given to this naive-Bayes classifier, and it is classifying it correctly. So recently US and UK are also using it for COVID-19 cases, whether there is a chance of recovery or not. So they are applying the machine learning techniques all over across the world. Okay, so new instances can be classified by combining the prediction of multiple hypotheses weighted by their probabilities. And even in the cases where the Bayesian methods prove computationally intractable, they can provide a standard optimal decision making against which the other practical methods can be measured. So even when we can't apply the Bayesian learning methods for some of the problems, but it gives us a standard optimal solutions when we compare it with the previous algorithm. So let us see what are the difficulties in applying Bayesian methods. So first, practical difficulties. So we should have initial knowledge of probabilities. If you don't know what is probability, and if you don't know how to calculate the probabilities, then using this algorithm becomes very complex for you. Okay, and when these probabilities are not known in advance, they are often estimated based on the background knowledge or previously available data and assumption about the form of the underlying distribution. So you should know all these things. What is the background or knowledge of that data, what are the previous data available on the particular problem, and then we can assume certain things on the distribution. And second practical difficulty, that is the significant computational cost, okay, required to determine the Bayesian optimal hypothesis in the general case. So as you know that the probabilities, again, it is more complex, so it will take more computational cost. So computational cost here in terms of is nothing but it takes more time to classify the things correctly. Okay, that's a cost, and it requires high-end machines, like high hardware support and software support. Okay, so these are the difficulties in Bayesian methods. So next we will see what is Bayes theorem. So this is actually the basic of any Bayesian methods. So the name Bayesian methods came from the Bayes. Okay, Bayes theorem. So he is a scientist. Bayes is a machine learning scientist. So what he has done is he has given a theorem based on the probability, where by applying this Bayes theorem we can observe we can differentiate between the datas, observed datas, and the data which is non-observable. Okay. So in the machine learning we are often interested in determining the best hypothesis from some space, some given space, that is H, that is nothing but hypothesis space, given the observed training data D. So this is the main aim of any machine learning algorithm. What we want is we always want the best hypothesis from the hypothesis space given the training data. One way to specify what we mean by the best hypothesis is to say we demand the most probable hypothesis. Okay, so best hypothesis is nothing but most probable hypothesis. Most probable hypothesis is nothing but the hypothesis which is giving you the good result. That is called as most probable hypothesis, or the hypothesis whose probability value is very high. Okay, we can tell in that sense also. The hypothesis whose probability value is very high, that we can call it as a most probable hypothesis on a given data. And to apply the probability, what should you have? You should have the initial knowledge. You should have the prior knowledge of probabilities. So Bayes theorem provides a direct method for calculating such probabilities. More precisely, Bayes theorem provides a way to calculate the probability of a hypothesis based on the prior probability. So you can calculate the upcoming probability by having the knowledge of prior probability. Okay, the probabilities of observing various data is given the hypothesis and observed data itself. So to define the Bayes theorem, first you should have to know some definitions, little notations and definitions. Okay, this P of H, it is nothing but the probability of the hypothesis. Okay, P of H is nothing but the probability of hypothesis that we can observe for a training data. So P of H is also called as prior probability. It is also called as a prior probability of H, and may reflect any background knowledge we have about the chance that H is a correct hypothesis. So here this P of H is called as prior probability because it depends on the background knowledge. So background is nothing but prior. Okay, so hence it is called as a prior probability, and for any given problem you should have some background knowledge. Okay, if we have no such prior knowledge, then we might simply assign some same prior probability to each of the candidate hypothesis. If you don't know, or if you don't know about any of the if you don't have any knowledge about the given data, then what we can do is you can simply assign some values to each and every hypothesis. Okay, and please remember that you can assign the values, probability values, in between 0 to 1. Next, P of D. This is another notation. P of D is nothing but the probability on the training data set. Okay, D is nothing but the training data. It is also called as a prior probability on the data set, that the data that will be observable. Okay, next, this is called as, or this is pronounced as P of D given H. This is, don't call it as D bar H or D divided by H. It is P of D given H. That means probability of observable data given some hypothesis. Okay, as you can see here, it denotes the probability of observing data D given some word in which the hypothesis H holds. Okay, so next, another notation is P of X given Y, where X is given and you have to it is called as probability of X given Y. Y will be given and you have to find out the probability of X. In machine learning, we are interested into finding of probability of H given D. So always in the machine learning we want to find out the best hypothesis given the training data, right? So it is there, always it is there. So it is there in the finest algorithm, it is also there in the candidate elimination algorithm, ID3 algorithm. So you can take any algorithm what we want in the machine learning is we want to find out the best hypothesis given the training data. Okay, and next, this P of H given D is called as posterior probability. Okay, it is called as posterior probability, exactly opposite of D given H. D given H is called as prior probability. Here it is H given D is called as posterior probability. Why it is called as posterior probability is, here what we will do is we will give data set, then we can calculate the hypothesis value. Okay, so hence it is called as posterior. Before only we cannot calculate it. Once the data will be given to you, then you can calculate the hypothesis value, or then we can see which hypothesis is giving you the best result. Hence it is called as posterior. Posterior means afterwards. Okay, before giving the data it is not possible. Okay, so I think you might have cleared with the notations, all these notations. All these notations are very important because these notations we are using it in our Bayes theorem. Okay, look at the Bayes theorem. So this is the formula of Bayes theorem. We are interested to calculate the probability of H given D. Data is given to you, data set is given to you, and you have to calculate the hypothesis H. That is equal to, this is prior probability, yes or no? This is posterior probability and this one is the prior probability. So probability of data given hypothesis into probability of hypothesis divided by probability of data set. Okay, so probability of H given D is equal to probability of D given H into H divided by probability of D. So this itself is called as Bayes theorem. Okay, so notice that posterior probability P of H given D reflects the influence of training data D in contrast to the prior probability P of H, which is independent of D. Okay, so please remember this Bayes theorem, which is very important for your exam point of view. And always the value of D given H will be given to you, P of H also will be given to you, and P of D will be given. So you need to calculate P of H given D, which is called as posterior probability. Okay. So as one can intuitively expect, P of H given D increases with P of H and with P of D given H according to the Bayes theorem. So according to the Bayes theorem, if the value of P of D given H and P of H increases, then definitely posterior probability will increase. If the value of P of D also increases, then it is inversely proportional, yes or no? So if the probability of D is increased, then probability of H given D is decreased. Or I can also say that if the probability of D is decreased, then definitely P of H given D will increase. Okay, in that sense also I can tell. It is also reasonable to see that P of H given D decreases. So as I said, as P of D increases, because it is inversely proportional. Okay. In many learning scenario, the learners consider the set of candidate hypothesis H and is interested in finding the most probable hypothesis of the hypothesis space. Okay. So already I have told it many times, what we are finding, or what is the aim of machine learning algorithm is, we have to find out the best suitable or best probable hypothesis from the hypothesis space given the training data. So given the training data or given the observable data. Any such maximally probable hypothesis is called as maximum a posteriori. Okay, so that maximal probable hypothesis is called as maximum a posteriori, which is also called as MAP hypothesis. Okay, so how we can calculate this MAP hypothesis, maximum a posteriori hypothesis? It is, so we can have the formula, that is H map equal to arg max. H belongs to capital H. This H is nothing but hypothesis, one hypothesis, and this capital H is nothing but the set of hypothesis, which is called as hypothesis space. Okay, so H belongs to capital H, P of H given D. So what is P of H given D? It is Bayes theorem. Okay, P of H given D equal to, what is the formula? So P of H given D equal to P of D given H into P of H divided by P of D. So substitute it here. So in place of this I can substitute that formula, which this is nothing but the Bayes theorem. So I have substituted this, and then this P of D has been eliminated here, because on a particular data, on a particular hypothesis, this P of D is constant. So as you can see here, notice that in the final step we have dropped the P of D because it is constant on independent of H. So it is constant, hence we can remove it or we can eliminate it, and this becomes the formula for HMAP, that is maximum a posteriori hypothesis. HMAP, maximum a posteriori hypothesis. Okay. So in some cases we will assume that every hypothesis in the hypothesis space H is equal probable priori. Okay. In some cases what we will do, if we don't have any background knowledge, then what we will do is we will assign the equal probability for the each and every hypothesis which is present in the hypothesis space. Okay. So then in this case, if we assign all values, equal values to all the probabilities, then it is called as the P of D given H is often called as likelihood of the data D given H. It is called as likelihood. P of D given H is called as likelihood of data given H. Okay. So it is also called as the maximum likelihood, ML. Okay, it is also called as ML, that is called as maximum likelihood, and it can be calculated by using formula HML, that is maximum likelihood equal to R max of P of D given H. Okay, P of D given H. Please note down this all formulas: Bayes theorem formula, maximum posteriori hypothesis formula, and this is maximum likelihood hypothesis. Okay, so three formulas are also very important. It is called as maximum likelihood hypothesis. In order to make clear the connection between the machine learning problems, we will introduce the Bayes theorem above by referring to the data T as a training example of some target function and referring to the hypothesis space as a candidate target function. So if you want to find out any of the probabilities for a given data, what we can do is we can apply the Bayes theorem, and we can check which hypothesis is directing me towards the target function, or which hypothesis is giving me the best result as that of target function. In fact, the Bayes theorem is much more general than suggested by the discussion. It can be applied equally well to set or to any set of hypothesis H of mutually exclusive proportion whose probabilities sum is equal to 1. Okay, so mutually exclusive, later I will give you the example what is mutually exclusive propositions. Okay, so one example here it is given is exactly opposite. Mutually exclusive means exactly opposite. If I say yes and if another says no, that is called as mutual exclusion. Okay, so he is telling sky is blue and its mutual exclusion opposite, exactly opposite is sky is not blue. Okay, one example here it has been given as a cancer patient example. So as I have already discussed previously, we can apply this Bayes theorem on each and every particular field. So previously he has given the pneumonia as an example. Here he has taken the cancer as a discussion, and for this cancer data he has applied the Bayes theorem. Look at this. Does a patient will have cancer or not? So we have to detect whether the patient will have cancer or not given the data set. So if we want to predict whether he can have cancer or not, what we will do is we will apply the Bayes theorem. Okay, so Bayes theorem will give us the probability, and if the probability is high, we can definitely tell that he may have the cancer. If the probability is less, then we can definitely tell that he cannot have the cancer. Okay, so look at this. A patient takes a lab test and the result comes back positive. Okay, the test returns correct positive results only in 98% of cases. So he is telling that he has given some test and test comes out as a positive, and in the 98% of cases we will get it as positive. That means what is the negative? So in 2% of cases we can get it as, even though it is positive, we can get it as a negative. So same thing is happened with the corona also, COVID-19 also. So if we go for RT-PCR, if you don't have any symptoms also, sometimes the result will come as positive, which is called as false positive. And sometimes if you have all the kinds of symptoms, but the result will come as negative, which is called as false negative. Okay. So these are the medical terms: false positive, false negative. Okay. So 98% of cases in which the disease is actually present, and correct negative result in 97% of cases in which the disease is not present. Okay, if the disease is not present, then it will give 97% of the time it will give correct result. Okay. So furthermore, 0.008 of the entire population is having this cancer. Okay. So look at this. He has written it as P of cancer. What is the probability of cancer? That means what's the entire population will have 0.008% of cancer. Okay, that's the P of cancer. What is P of negate cancer? Negate cancer means exactly opposite of this. This is called as mutual exclusion. So it is 0.992. Okay, if you subtract it by 1, it will give you 0.992. So then next, what is the probability of positive given the cancer data? So what is the probability of positive given the cancer data? It is 98%. 98% is nothing but 0.98. Then exactly opposite, what is the negative given cancer? It is 0.2. Okay, 0.2. Sorry, 0.02. Okay. So next, what is the probability of getting positive value if he don't have cancer? What is the probability of getting positive value if he don't have cancer? Look at this. Look at the statement correctly. See, it is giving you negative result if you don't have cancer. Okay, how many times it is giving you? 97% of time it is giving you negative result when you don't have cancer. That means if you don't have cancer, then what is the percent of positive? Okay, 97% it is giving you the correct result. So you are not having cancer and it is negative. So it is 0.97. Look at this. This is very important here. So negative when not having cancer is 0.97. That means positive when not having cancer is 0.03. Okay. So after getting all these values, we can apply the Bayes theorem and we can calculate the posterior probability. So that is P of cancer given positive is equal to, so apply the Bayes theorem. So P of positive given cancer into P of cancer divided by P of positive. Then similarly for P of not having cancer plus given positive is again same formula, Bayes theorem you can apply and you can solve this. Okay. So this example that we have taken, it illustrates the probability of getting the positive or negative result in the cancer. Okay. So we got the value. So first, probability of positive given cancer is 0.0078 and probability of positive when not having cancer is equal to 0.0298. Okay, so these are the value. If you apply, then you will get it. Okay, so we'll stop here with this example. In the next video, I will continue with some more examples of Bayes theorem. Okay, thank you.